I guarantee you've seen things like this scribbled on a chalkboard. They look kind of different, right? But they actually belong to the same exclusive family. So, what's the secret connection? What's the rule that lets them both into the club?
Well, it turns out the secret is surprisingly simple. It all comes down to one little detail. The powers, the exponents that are attached to the variable, the x.
And here's the rule, plain and simple. For something to be a polynomial, the power on the variable has to be a whole number. 0, 1, 2, 3, and so on. So an x squared or a 2x, they're in. But what about the square root of x? Well, that's really x to the power of 1/2. That's a fraction, so it's out. Same for 1 over x, which is just x to the power of -1. Not a whole number, so it's not a polynomial. This rule is what makes polynomials so reliable and predictable when you graph them. No weird jumps or sharp points.
So we know the rule to get into the club. Now let's see how everyone's organized inside. It's kind of like there's a ranking system, a whole hierarchy, and it's all based on those powers we were just talking about.
And that ranking system is all about something called the degree. It's super straightforward. The degree is just the highest power you can find on the variable in the whole expression. That one number tells you almost everything you need to know about it.
So let's look at the power rankings in action. If the highest power, the degree, is 1, like in 2x minus 3, we call it linear. Makes sense, right? Because if you graph it, you get a straight line. If the degree is 2, like in x squared plus 5x plus 6, it's a quadratic. That comes from the word quadrate, which just means to make a square. And if the degree is 3, you've got a cubic. These are the big three you'll see all the time.
Awesome. So now we can spot a polynomial and even classify it. Let's switch gears and actually put one to work. Our next mission is to figure out how to find its specific value.
Let's tackle this with a hands-on example. So we've got this polynomial, p of x equals x squared minus 3x minus 4. The mission is simple. What is the value of this whole thing if we decide that x is exactly, specifically, the number 2? The way we solve this is pretty simple. It's just a plug and play. Everywhere you see an x, you just swap in the number 2. So that gives us 2 squared, minus 3 times 2, minus 4. Then we just do the math. That's 4 minus 6 minus 4, and we get our final answer. And there we have it. The value is -6. Now, finding this value is useful for sure, but in the grand scheme of things, this isn't usually the ultimate goal. The real hunt is for a much, much more interesting number. And this right here is where everything gets way more interesting. Because in the entire universe of polynomials, there is one magic number that we are always searching for. Forget -6 for a second. What if we plugged in a number for x, did the math, and the answer was 0?
This is the bullseye. This is the whole point. When we find a number for x that makes the entire polynomial shrink down to 0, we found it. That special x value is called a 0 of the polynomial. And that, my friends, is our real target. So let's be crystal clear on this. A 0 is like the solution to the puzzle. It's the one specific number you can plug in for x that makes the whole thing perfectly balance out to 0. Honestly, finding these zeros is one of the most important jobs in all of algebra.
And here is where our two big ideas slam together. Remember the degree, the power rankings? Well, it does more than just give the polynomial a fancy name. It gives us a huge clue. The degree tells you the absolute maximum number of zeros that polynomial could possibly have. So a degree 2 polynomial, it can have up to 2 zeros. A degree 3, up to 3. It's like a roadmap for our hunt. Which leaves us with this final, big question. We now know a quadratic has a degree of 2. We know that means it can have up to 2 of these special zeros. We even know why those zeros are so important. So the only question left is, how in the world do we actually find them? That's the next part of the code we need to crack.